So today's lesson, as I was just telling my class, is about more separation of variables. In the Larson text, this is going to be 6.3. So we're going to practice separating variables on some problems that might be a little bit tougher. I don't know. It's really hard to make separating variables tough. So we're going to do a few of these. And then we're going to lead into, also in this section, the logistic equations. That's going to be in my next video, and you definitely want to look at that. You want to do a little bit of reading out of the book first. So let's just jump right in. All right, so I think this is a possible differential equation. Why is it a differential equation again?
dy dx.
It's got a derivative somewhere in it of some type, some order. Okay, so I want to separate variables. If I can I do so? I think so. What do I want to move? Multiply by dx, and this,
Divide by 1.
the whole chunk gets divided to that side, and the y gets divided to this side. Okay, so I'm just going to do that all in one step. It's not going to be super sneaky, I don't think. You guys ask me if you have a question. So we'll have dy over y here. That goes over here, right?
Yeah.
We've still got our x. We're going to multiply our dx up.
Yeah.
But this also, this whole quantity
X over x squared plus 4
gets divided, right? So then that has the x, dx multiplied up.
Yeah.
So there we go. Now it's nice and separate. That's the whole crux of the technique separating variables. The last thing we're going to learn next week, I think I have one big last thing and one small last thing. The big last thing will be one other different way to solve different kinds of differential equations, one kind that cannot be separated. Because sometimes you just can't separate it, it's just not possible. Okay, so this one you can separate those, so I now integrate, right? Integral on the left side is, you've seen that lots of times, right? Natural log. And this side, what do we have on this side? Let's do the integral.
X squared over 4x.
What kind of integral is this? Arctangent? U substitution? Split up the denominator? It's a U sub, right? So I'll write out my U sub over here in red. So U is what?
X squared plus 4.
I think you could probably do this one in your head. We'll write it out today. Du then is
X 2x. So d over 2, so 1/2 the integral.
So x dx is du over 2. So that's du over 2. 1 over u, which is going to be natural log of u. You got it. All right, so I'm going to switch back to blue.
1/2.
And I get the natural log of u and a half. So that's half the natural log of x squared plus 4.
Plus c, right?
Plus c, totally. Okay, if I want to solve this one explicitly, I don't think that's very hard, so I'm going to in this types. You always want to try to solve them explicitly. The AP exam always demands you do that.
Base e.
Yeah, we just want y, so if we just go with a big E on both sides, we'll get
Y is equal
y equals.
e to the 1. Oh.
Now, what was the trick we used before on problems like this? Very important trick.
1/2 power.
It's kind of like you think about it like this, right? And that's a constant, but I really still can't do that. This 1/2 is in the way. Can you like do something with the 1/2? That's a logarithm, right? So I can put it up in the logarithm. In fact, 1/2 power is square root. There we go.
So e to the root.
So that's a constant. Let's call it like, you know, I'm going to say this was a temporary constant. So I'm going to say this is big C. That sounds better to me. And then e to natural log goes away, and we have this left. That's the general family of solutions. If we were to drop an initial condition somewhere, we'd get a particular solution in that family on the slope field or whatever you want to think about it. Okay? You guys also have some slope field problems this weekend. I gave you that worksheet yesterday, right? So we've got a few slope fields that should go really fast. Okay, there's one. Let's do another. Okay, can that one be separated? Well, I put it in this section, so probably better to write this as
u sub.
dy dx. I don't know if we need a u sub. Maybe we will. Let's see, Parker. So if you have dy, that's going to be...
Okay, multiply by dx and then divide by sine, right? So it's cosine cotangent of x dx.
Right?
Integral.
Now, you might not remember the integral of cotangent. That's one of the harder ones to remember because it's just not that common. So it might have been better, instead of writing that as cotangent, to just leave it alone, right? Do you remember it, Emery? Should remember tangent, but that's negative natural log of cosine, so it's positive natural log of sine. Let's just do it, though, just in case we forgot. Did you do it with the u sub? Very good. So if you go like this, then derivative of sine is cosine, and oh, it's just sitting right there. So that's going to be the integral of 1 over u du. So that's natural log of u, which is natural log of sine, like Jamie said. Plus y plus c. That one was pretty boring, I think. You could also just remember cotangent's integral. So, okay. Let's do another one. This one's longer. I don't know if that means it's going to be harder. If we can separate it, I think we're going to be good. So I'm going to get these ones out of the way. Okay. So I've got an initial condition. We'll find a particular solution in this family. But let's solve it for the general solution first. So can we separate this guy? There's kind of stuff all over the place. So you might be thinking this is not separable. In fact, it looks more like what I'd call an exact differential equation, which has another method. But I'm not going to teach you that method this year. I think you could separate it because that's 0. If it wasn't 0, we'd have problems.
The second big chunk of the other side.
Totally. You've got it. Just move that second big chunk, like Emery said, to the other side.
Don't you want to multiply or divide by e to the x squared also, because you want dx, or you want x's with x's and y's with y's.
Good, so now I can separate it. Yeah, you're right. I think you probably want to take 2 steps here just to be careful. I already made one mistake. Where is it?
Negative.
Okay, so now separating.
Divide by y.
The y's are kind of already over here. I'm going to stick on that side. You guys know what I mean? So I think I'm going to divide that way. You're right, Parker. And then move this way.
Yeah.
So we'll have x over e to the negative x squared dx. And over here we have y squared minus 1. That y is going to go to this side, and we've got dy over there already.
I have a question about that.
Yeah.
Does that actually work? Because if you divide by y, you have e to the negative x squared over y, right?
I guess if you want to have it like that, yeah.
Shouldn't it be negative e to the x squared?
It should, right. I have another mistake, right? This should have been negative, right? So I guess I'll just fix that. Thank you. Yeah. I made 2 mistakes. Didn't do that one on purpose. So Parker, are you still uncertain?
No, I think I got it.
It's hard to see with this equals in here. So we're going to integrate now, okay? So I'm going to take that over here. Let's simplify. Can we simplify on the left before we integrate? I think we should.
You do u sub.
Before we do that, we'll do u sub though. Yeah, you're right. E to the negative x on the bottom?
Put it on top.
That's the same as e to the positive x squared up top.
So it's x e to the top.
We've got a negative and we've got an x dx. That looks friendlier, I think. And then on the right-hand side, what do we have? Break it apart. Yeah, so that's just going to be y.
Ln y.
Don't get ahead of yourself.
That was
Simplify before integrating, right? Oh. Weather shenanigans. Wow.
Yeah, that was
It's amazing. This is amazing. You're getting a nice introduction to Colorado this
You
year.
can pull the negative out.
What should I do?
Pull the negative out on the left side.
Okay, yeah, all right. And then should we u sub that? Can you guys zen it? Or no? What is u supposed to be? X squared. So what's the thing from the chain rule we're going to have to cancel out? We're going to have to put a 1/2 to compensate for the times 2. So I think I would just do that one with that. So it's going to be 1/2 e to the u, which would be this. If you don't like that, write u as x squared and do the u sub. Okay, so this has a plus c. I guess I'll call it c1. Over here, the integral of y is
y squared over 2.
Y squared over 2.
Natural log of y plus c.
and this one is natural log, and then this one is c2. So usually we solve for y. It's since this y is like locked in a logarithm and that one's there, solving this explicitly for y would be really, really difficult, if not impossible, probably just really difficult. So I think we're just going to leave this one implicitly like this, except let's just absorb these constants onto one side, say like plus c like we usually do.
You gave us the value though.
And I've got an initial value, so I can kind of clean that up too. So if I put 0 and 1 in, 1 is the y value, 0 is the x value, right?
Yeah.
So I'm going to say this is going to be negative 1/2 e to the 0,
yeah.
squared is 0, plus c. Y over there is 1, so that's 1/2, because 1 squared is 1.
Natural log of 1.
Minus the natural log of 1. What's natural log of 1? If we remember that that's 0. So this says 1/2 e to the zeros, of course.
1/2.
1. So c is equal to
0. Wait, no. 1.
1, right? Add a half, you get 1. There's the specific curve in the slope field. Okay?
I don't see the negative.
All right, let's do one more. I think this is another problem where we can use separation of variables to answer their questions. They say find an equation of the curve that passes through a point and has a slope. This is kind of going back to the beginning of calculus where you started thinking about a derivative and a slope, but you can think of it as a differential equation as well. It says it has a slope of this. So what does that mean that the curve has to satisfy?
The relationship between quadrats.
Right. Our instantaneous slope at that spot, that's the thing for instantaneous slope, has to be equal to certain things. So we say that's the differential equation. You can think about it like that, or you can think about it like we did at the beginning of calculus.
Is it like that to your initial condition?
Exactly. And it's like this is our initial condition. So this is just another way to think about an old familiar problem, but it's good to be flexible. Okay, so if we're doing it that way, then what should I do next if I'm trying to solve?
Multiply by dx, multiply by x, then divide everything. Oh man, that gets annoying. Okay, multiply by dx, so then you have y dx. Divide by that.
Right?
Y.
Yeah.
Yeah, you can just switch them.
Okay, integrate. That's our good friend, the natural log again. What's this one? Very important to integral not to mess up. Remember it. If you're having trouble with it, remember you think about it like this. It's just a power rule.
Negative x.
That is a very, very important integral. I can't emphasize it enough. So super, super common. And people mess it up all the time. Believe me, I'm a calc teacher. I've seen it a lot. So watch out for that one, okay? So we got a plus c. Now, at this point, we could stick our initial condition in and find c. Getting like, my speech is blurrier the longer the year goes on this year. It's crazy. I'm stuttering. I think we should too. Anyway, since we're here, we'll do some calculus. So you could plug that in and find c right now, or you can solve for y first. You know, I think a lot of the time it's easier to plug in right now, and it's a little bit more obvious. So I'm going to do that this time. So the initial condition was 1, 3, so I should have what then? Natural log of 3, and the absolute value of 3 is 3, so 3, right? Equals negative 1 over 1 plus c, so that's negative 1. That's natural log of 3, so c is, in this case, natural log of 3 plus 1. So that's kind of an ugly c, but we can put it in there. Okay, so now I'm going to go back and solve it and see if we can clean this up just a little bit and get a nicer curve. That's pretty good. If you did that on the AP exam, you pretty much have all your points on a problem like this on an FRQ. So, let's see. I think I want to E it, don't I?
Yeah.
I'm going to use a different color. I don't have green.
Wow.
There's green. E.
So then it's y is equal to e to the negative x.
That's not e to the negative x, it's e to the that.
Oh yeah.
Times e to the that times e to the that.
But that's 0.
Does that make sense? Because those are all just added, right? So that
No.
cancels. So we get y equals 3e, because 1 doesn't matter here, does it? So it's 3e e to the negative 1 over x. There's the specific curve. That's a little bit different, but
Wait, can't you add the...
yeah, if you want to say that this can go back up in here and mess around with it more, you can. You can say, well, I don't have to write it that way if I don't want to. I could just write it as 3, and we had an e to what power, of course? 1, and say plus 1 right here if you like that better. It's up to you kind of which way you write that. All right, let's look at some partial fractions so that you guys can understand this really big, important derivation in the video for logistic functions. All right, so I'm going to look at a couple basic partial fraction problems. Now, there's different kinds of partial fractions. Since we don't need that many this year, I'm just going to show you the most basic kind, and we'll do 2 examples, and we'll call that good. Okay, so partial fractions are used for all kinds of things. They're basically a decomposition to change something that's complicated into small pieces and parts that you can do things with, like integrate. For instance, if I put an integral in front of this, you could try u subs and arc functions and all that stuff all day long, and it's not going to work. If you change it into smaller, easier fractions, it's really easy to integrate this problem, actually. So that's what we're going to learn today, is a new integration technique that we're going to need for this logistic thing in 6.3. And I'm not going to give you a whole lot of problems like that this year. It's just kind of an introduction, so that you've seen it before, that kind of stuff. All right, so we're not even going to think about integrating it. We're just going to change this complex fraction into partial fractions, okay? So, first of all, you want to think about, is there any factoring that can be done?
Yes, x minus 3, x plus 2 on the bottom.
Totally. One on the bottom is an easy factor, right? It's x minus 3, x plus 2. Good. Okay, so now what we're going to do is we're going to split that up. There's all kinds of different partial fraction techniques. Today I'm going to just show you the one for linear factors. These are nice linear factors, aren't they, on the bottom? mx plus b kind of things. So for regular linear factors, what you do is you say, well, I can make this into something else. I don't know what the tops of the something else are yet. I'm going to find those. And that's the way I can proceed. I can split that big ugly fraction into 2 smaller ones. And notice, if I put an integral in front of both of these, and these are just numbers, those are easy to integrate with a natural log, aren't they?
Yeah.
Very easy integrals to do. So that's one reason we use partial fractions.
Wait, but you can...
So the only question is, what are a and b to do that? So then you need to use algebra. This is just algebra. Sometimes I've taught it in algebra 2 even.
And then that thing
To make that
divided by
happen.
the opposite?
Say again?
It's 3x plus 11 divided by the opposite denominator that you're not using, right?
You can't really look at this and just like guess what it is. That's just way too much. The idea is that you can split it up like this, and you're going to figure out what makes it work.
Can you split it up into more than 2 parts? Like if it...
It depends on how many factors there are. We'll do one like that next. If this factored into 3 pieces, then we go A, B, C.
And you can only do it with the bottom factors?
Yes.
But how do you determine...
Well, even if the bottom was a quadratic that was not factorable, you could use the quadratic formula, turn the answers from the quadratic formula into factors, and then do this still.
That is nasty.
But that's something that's beyond what most problems ever call for. But I've had to do that in like certain high-level stuff before. Yeah, totally. So partial fractions, big time important. Anyway, good questions. We're just going to see a couple of them today. So how do we find a and b? This is an equation right here, okay? Let's just even forget about that part. It's an equation. It's got to be satisfied for not just one x value, but for all x values. So do what you know from Algebra 2 and find a common denominator. What's the common denominator of this equation?
Wait, just kidding.
You need that, and you also need
You need the
that.
opposite one.
So I'm not going to make this real messy by drawing a whole bunch here, but that's the common denominator for both sides, right? So take that and multiply through by it. So when you multiply through by it here, everything cancels, and what are you left with? When you multiply that common denominator here, what cancels? The x minus 3 cancels, and you're left with
X plus 2.
a, and you're also left with x plus 2. If you don't like that, then draw it in there the first couple times you do it. Gone. And that's what's left. So if I multiply through by it here, because if I do something to one side of an equation, do it to the other side everywhere, right? So if I do it here, what am I going to be left with?
X minus 3.
B and the x minus 3. And once you're good at this, this goes like lightning. It's like real easy. There's all kinds of ways to figure out a and b from this thing. The easiest way is to choose convenient values, like x equals what?
1.
What's a nice convenient value here? 1 is not convenient. It's a good guess because 1 is a simple number, but in this equation, it's not good.
3.
I think 3 is good. Why is 3 a convenient value?
Then you get rid of b.
Because then that goes away. We'll just have one thing to solve for. So you say let x equal 3,
So it gives you a positive number.
and you see what happens. So if you put 3 in over here, you get 9 plus 11 is 20. If you put 3 right here, you get 5. If you put 3 right there, you get nothing. So that killed off b. That's why it's convenient.
So a is equal to 4.
And that tells you what a is. Yay! Then you say, do I have any other convenient values? Now, in harder partial fraction problems, you won't. So you have to do other things, but we're not going to run into that today. So we'll just say x equals negative 2 is another convenient value. You see what happens. Negative 2 there is negative 6 plus 11 is 5. Show as much work as you need to for yourself.
0.
Negative 2 there killed a, so that's good. Negative 2 there is negative 5.
B is negative 1.
So if you divide 5 over negative 5, you get negative 1. So then that shows that this fraction is exactly equivalent, like our guide up there says, to 4 over x minus 3 plus negative 1 over x plus 2. One thing that's good for is you put an integral in front of those pieces and they're both immediately done. Integral of that's 4 natural log x minus 3. Integral of that's negative natural log x plus 2. This is useful for oh so much more than that. We're going to need that in logistics here in just a second. Okay, so let's do one more example of the same kind of thing and you guys can help me more with this one. I've got one more example. Pretty much the same kind of thing.
Mr. McGee,
Yeah.
how come it's 4 over x minus 3 and not like 4 times x plus 2?
I think you just need to do this for a while before you ask more questions like that, Parker.
Okay.
So when you get to Calc 2,
Like, where did you plug that back into?
Into the, like the first question.
Into the, yes, that's right.
Oh, okay.
We're going to do it again here. So let's do one more. I thought we needed 2 examples so you guys would be able to follow the logistic thing. Okay? So, first step. What should we do? If you're watching the video, pause it. Maybe try to work it out yourself.
X plus 2 on top. Squared.
Okay.
That's
Just
not
kidding.
factorable, but good try.
Back to the bottom.
The bottom, what about the bottom?
It's gonna be
3x.
It's going to be 3 different things if it factors. Hopefully it will, because otherwise we'll be stuck in the situation Rachel asked about.
One of them has to be
Okay,
3x.
so what do they share?
X.
There's part of it. Can we do more with it than that? Remember, this is where you can apply that
Yeah.
longer algorithm. That's kind of long. I think we're in calculus now. We might be able to just guess and check this. Should we try that way?
I think it has to be 3 and 1.
If you were me in calculus, then no, it wouldn't have worked for you because I was bad at
One of
guessing
them
and
has to
checking.
be 3x, one of them has to be x.
One of them has to be 3x. There's not too many guesses in this one. So one of them's 3x, one of them's x.
I think it's
4 has a
negative
few
3
choices. So Parker's got to guess. What do you want?
4 on, so 3x minus 4,
So he
3x
says,
plus, or x plus 1.
okay, let's check it. 3x squared, good. Minus 4x
This doesn't work.
plus 3x.
Nope.
That's negative 1x. We're looking for 4x. So
We
no,
do minus 2 plus 1, that's about it.
we could do like
No, yeah,
minus
it's plus
2 plus 2.
Yeah, that's it.
Gotta think ahead if you're gonna guess and check these.
Yeah, that's right.
That works. 3x squared, 6x minus 2x is,
Yeah. And you get minus 4.
yep, that's the right answer. There has been no partial fractions that has happened yet, right? The idea is now we're going to split this thing with 3 factors into 3 different fractions. That's partial fraction decomposition. So I'm going to say 3 fractions. X, 3x minus 2, and x plus 2. A, B, C, So if you're watching the video now, I would pause it and see if you can find A, B, and C for yourself based on what we've just done.
1, B is equal to 2.5, and C is equal to 2.
So there's the rest of that one. I just solved it, so you can pause the video and have a look at my work. Now you didn't have to do these in any kind of order, but those are the 3 convenient values I think you want to choose. This is true for all values, right? The equation has to be true for anything. These are just the convenient ones, and that's one way to solve this kind of situation. It's not the only one. So anyway, you should have gotten A was -1, C was 1/2, and B took me a lot more work. It took me a while to get 2.5 or 5/2. So that's how I wrote the partial fraction decomposition of that. Integrating this will be nice and easy, but also useful for lots of other things. So if you're at that point, what you want to do in our lesson is you want to now go and read 2 pages out of the textbook, just 2, page 427 to 428. You want to read them carefully. There might be a few steps in the math that are a little bit confusing, but mainly they're just going to introduce this new function called the logistic curve. It's basically a new function from the library functions in Algebra 2, which is going to become a lot more significant as we go towards next year. So go ahead and read those, and then after that you're going to want to watch my video on logistics, which I don't know if I have an updated one or not yet, but has some really good stuff in it as well. See you next week.